Yeah.
Yes.
Can you see my screen?
Yes, yes. I was talking on mute. Sorry. Yes, we can see your screen. Do you have to run everything again?
Yeah, I've just opened the notebook now.
And will you need to change, like write everything again or not?
Uh,
You
no,
edited.
this is the one
Oh, okay.
that I
Then
ran
it will
last time.
most probably it will be saved. You can actually try this view recommended plots, and you can the above one. Yeah, so you see the view recommended plots. If you just turn it on, uh, it will generate plots on its own. Just turn it on. Yeah,
Oh,
and it's
okay.
actually nice feature. You can see which event occurred at what time. You see this time versus event type. This green plot. Yeah, you can see like
Oh,
the no, you can open
what
it.
does it say?
So if you click it, it will create another cell which generates this plot. Yeah. So this is basically uh, four number event and two number event or something like that. But you can
Oh,
broadly see here like majority of events occur in one third, first one third of the session, then middle of the session, and then last. Again, there are some patches where nothing occurs. So, I just found it very interesting feature. Like they can create plot on their own. Like it's a code written basically. If you run that show code, yeah, you can probably do plot series. Okay, yeah, yeah. There
there
are
are
others
others
as
as
well. Means
well.
I found it interesting to share that this is a useful feature. That
Time versus event type.
uh,
That this is also
correct.
a good one. So four is the record.
Four
Four
is
is the
the
recording event type.
lick. Basically, whenever it licks the port for getting water, it records that.
Okay.
And two is the press, three is the tone, like that.
Okay.
Yeah,
Okay. I'll move ahead then.
yeah, this is fine.
So I actually plotted this
Oh,
frequency response
oh, that's
for
nice.
different filters. So one is Butterworth, one is
Okay, okay.
Chevy Chev. And so I have not labeled it properly. So this blue one
Butterworth
is
filter.
the Butterworth filter, and this orange one is the Chevy Chev filter.
Hmm.
Both are same
So
order.
Butterworth is like centered on that particular value, and Chebyshev is
Yeah. So
like it is right only greater than those frequency will be attenuated. Otherwise, it's one probably
yeah. Also, it exceeds this 30 hertz. I mean, this horizontal
cutoff
dashed line is the yeah, minus 3 dB
70%,
cutoff.
68 point
Uh,
something percent.
well, yeah. In this case, it's 1/√2 cutoff. And so,
So it exceeds that, but not by much. It is very steep. It is very steep. Like
yeah, not very much. Yeah, very steep.
okay,
So actually, this if you allow for more ripples in this pass band, then this will be
oh I see.
even steeper.
That
So,
changes the signal.
but
Yeah, that
that
changes the
that would be of
signal.
no use, right? Yeah. So yeah. So let's say it's
Oh,
yeah. So it's very bad.
so why
It's
is
cheap,
this so?
but
Why can't
then
they keep
the thing.
straight line here? What's the
I think it has to do with the
okay?
design of the filter. I mean, for I think any filter, there's a trade-off between the passband ripples and the what do you call it? This steepness, the roll-off. So Butterworth case is it's not the roll-off is slower, but it doesn't have any ripples. But to reduce the
It
ripples,
becomes like
then
list. That's nice. Is Aroshi?
but the Butterworth filter, I think in our case, it should. I think this would be better. So yeah, let's move forward.
Can you share that piece of code? I can include it in my in the chat box if you put. I will include
Yeah,
the labels.
think you need to modify. Yeah, and also I thought of plotting side by
So I
side,
will
but
modify the
then
subplot 1
the
comma 1.
differences were not that clear.
He's showing some interesting stuff you should see. Okay, I'll put it. Hmm.
And yeah, order might also be different. I haven't checked. So let's say fifth order. It is hard to compare looking at it like this, but yeah,
Yeah, done.
yeah. So
If you
the
increase the order
roll off becomes
or decrease the
slower.
order, of course.
It decrease the order.
Hmm. It becomes very less step. If you do 2, it will be like 45, the cutoff frequency.
But with the Butterworth filter, I think it maintains the cutoff at what you give the value 30 hertz. If you give it, then it maintains the 1 hour
Correct,
route to
correct,
cut
correct.
off there, whatever be the order or
It's centered around, means not centered, but cutoff is there. Okay.
try a 10th order filter.
Yes.
Very steep.
Hmm. Correct.
Yeah, so let's
So you tried Chebyshev.
move ahead.
Okay.
No, Butterworth.
This is denoised.
Yeah. And this is the correlation between E and I denoised.
Yeah. Here we left. No. After this we left.
Yeah, so this is the high pass filter. So here also, I think there was some. No, this was just
No, no. There
to
might be
run.
some. You would have filled that. There was some.
Yeah, yeah. So here also, we tried a Butterworth filter, and it's a second order. The cutoff frequency is 0.05 hertz.
And you can
And yeah, then
actually.
this will apply this
Uh,
filter for
yeah.
both the.
What we are doing is just getting that mean to be 0. Rest every frequency will remain the same, I guess. Only 0.05 is too less if you see that frequency plot. The the frequency plot. Yeah. This one. No, back. Down. Not this.
uh, this frequency response. Yeah, yeah, let's try this.
Make it high. 0.05. It's a second order filter. Second order. Okay.
Yeah, this was it's a second order.
It's really not sharp. Haha, it is. It is sharp.
It's a very sharp. Maybe we can zoom
Is
in
it the case that for high
to
pass,
that.
when you decrease the order, it becomes sharper or something like that?
I'm not sure about that. Let's try 0 to 1.
Hmm.
Yeah, so this is it. I think it's slightly higher than 0.05. The
For
1 over root
this
2
is
cut off.
same for both Chebyshev and it's actually same. Yeah, exactly same for Chebyshev and the cutoff seems to be 0.1 or something. So 0.1 hertz is what?
This is a high pass.
Kind of.
Exactly the
0.1
same.
hertz means every 10 seconds one event. So
One every 10
hmm,
seconds.
those kinds of frequency we will attenuate totally with this filter. The tonic. So yeah, so what happens that in
So it's
this
fine.
photometry, it's a not very good technique for. It's not a very good technique for tonic recordings. Tonic meaning at like above seconds or in minutes level. You can't record them very reliably. You can record phasic changes very reliably. Phasic meaning on a 100 millisecond scale. So that's for like longer recording. Either you use like voltammetry or something like that. Chemical techniques where you actually take concentration of chemical at particular intervals and then measure. But there are now new analysis methods that have come up uh, in photometry also to make it more reliable on tonic scales. So it is something related to how photons are released when light is shined. So some time gap is there, and utilizing that time gap, they can actually measure tonic levels of dopamine, or any in any biosensor they can measure tonic changes. The method is called flip or flim. Like these two methods are there, I guess. You can look it up if you want to. Flim method or flip method.
Okay. So why is it that
Because mainly because photo
fiber
bleaching.
photometry cannot measure the tonic changes?
Like if you correct for that, and if you want to do high pass filter or something, then you can't record it very reliably. Means if you have isoasbestic and you don't do a high pass filter, then you can still record some tonic level changes, but not entirely. Yeah, we are filtering that out with high pass filter.
Okay. So we're filtering that out with high pass filters.
And also our we'll see now in the next cell, uh,
Okay, so let's proceed.
like the scale that we use is df over f, right? So that over f itself will
Yeah.
uh, like it will incorporate all tonic level changes, and you will not get that out of df over f. So yes, we need some other analysis methods for this. So it not only analysis, but different hardware also. So it not only records intensity, but also time delay between certain light, excitation and emission. Those kind of hardware is also required. But it is an upcoming advance in the field. Yes. Okay. Go down. You applied the high pass filter. Here you can remove that X-lim and you can
Maybe
see
I've run.
everything is now like at zero. You can like, yeah, everything is centered around zero. And if there are these no lines now,
Yeah.
blue lines or red lines, then you could probably sense that whenever there is large movement in the, you see that the width of the green portion reduces when there are no behavioral events. Like it
Yeah.
increases when there means overall you will see that. So overall, yeah, yeah, it is like shallower. So the dopamine activity
In this
reduces
part.
when it is resting or it is not doing any movement. When it is not doing task, it is either grooming or eating. Then dopamine will come. But when it is not doing anything at all, then it will be shallower. So those kinds of things are also clear from this, but not tonic level. Like you can't get those wave like thing or something like what percentage of change. You can only measure average level, like from phasic changes.
Okay.
So correlation coefficient is
So yeah, then
0.244.
this is the linear regression part. Yeah, so
Mm-hmm.
this is
Yeah.
I calculated between I and E. Yeah,
Haha. So
I mean this is not
that's true, and
much,
that's what
right?
we want. If it is not much, then there is something related to like other factor
Yeah, because
uh,
yeah, the signal.
that is also yes,
Yeah, yeah. If it was higher, then uh,
yes,
it would
yes.
follow the same isosbestic and excitation would follow the same. pattern. So linear regression, this is when we,
That is
so
the
what is
excitation wavelength,
CH470?
channel 470.
Okay. So here we're using the choose the right data to fit the regression model. We're using the high pass filtered denoised signal, both isostatic and excitation, and fitting the model using these two. And so this prediction is what the model predicts. And finally, to get the motion corrected signal. So
Yeah,
this I had it out. This is correct, right?
actually, Arushi can show a very
Prediction.
interesting plot of
Yeah.
from her data. Okay, so her data was basically uh, some flaw was there in the recording, and it could she couldn't get the signals. And in the correlation plot, you will not see such spread. You will see a pure like a straight line, just straight line. So there is no signal there in her data. So it was an example of a session where
Okay.
uh, there was no signal. She's starting presentation. Okay, we both can present together. That's nice. Yeah, yeah, I can see. Ah, this plot. Yes.
Yeah, I can see.
Yeah, I just wonder
Oh,
if you are
so
plotting the same thing
exactly
twice.
a
Can
straight
you
line.
check? Go down, go down.
Yeah, yeah. The
Yeah.
data is both are I denoised
No, here. Plot dot scatter x comma y. Y is
above the.
e. Yes. Yeah, still means there are, it follows some straight line pattern, and then there are some points which are outside that straight line. It's weird. So this is
Yeah,
uh, I don't know what happened in between the session, but uh, this is very weird. What is this points in the below the line? Don't know. Oh, yeah, these are the last few points, I guess. If you remove them, it may give you some signal. You should put the uh, condition in the first place. In the first few cells, you put the condition, right? Greater than 0 time. So you also put less than some time. You don't get like that. These are most probably the last few items. So in last few minutes, when you turn on and off the photometry LEDs, there is some time gap. Like you turn off isosbestic first or excitation. So those kinds of points come up, show up like this.
okay.
Yeah, but otherwise, if you see the main part, it's like more or less straight line. Anyway, you can present the next
Yeah,
few
it's
cells.
almost follows a straight line.
Okay. Prediction.
Yeah. So the next is the visualization
Yes.
of this.
So for this you use that 620
denoise with its
wala
prediction.
range.
Why not?
The set the X limit to that 620, you will see that, yeah, these kinds of patterns you see, those kinds of patterns are movement related patterns. They are captured by this prediction. So those will be lost when you subtract this, right? Because the this predicted is a linear
How do
function
you
of
know these are
isospastic,
movement
right?
related patterns?
So basically, this prediction is a isospastic signal scaled to high pass, scaled to this 470, right? So I this these patterns reflect in both the channels,
Yeah,
and that means that it is movement related or some other artifact which is common to both the channels and not dopamine related, basically. Okay.
okay.
Okay. Now not many cells are left.
So yeah, this is
You can just
as
run
much as
them.
I have done.
Arushi, do you have loaded data you want to run? No? Oh, she is listening. So what can you say from residual plots? Why are we plotting residuals against prediction? Why are the residual not pure noise? So we already discussed this, like it's not pure noise because there are other factors which are responsible, right?
Yeah, to
Not artifacts.
yeah,
Artifacts are covered in this. That's why, like, residuals means what
artifacts
is
are also
left,
there.
which we can't predict from isoasbestic. So what is left is actually contains some meaningful data. It's not pure noise, and it's good news for
Okay.
us because if it is pure noise, basically in case of Arushi's data, it will be pure noise. That doesn't mean
Yeah,
like that means that there is no signal there. Here we actually see that it is a there is a positive shift to the residuals, and it's not centered around zero. It also has a pattern that it's like this, but more positive when it is the predicted value is zero.
yeah.
Uh,
I actually thought this is the same thing as this, just it has been
no,
rotated to
rotated means
zero.
yeah, rotate yeah, exactly. So yeah. Correct, correct. This same thing as that. Yes. Correct. Same thing.
Yeah, because we are
Good.
subtracting the prediction.
That's why we discussed that already. Okay. Then that is also we have already done because that is nothing but
Yeah, this is
um,
the motion corrected data with
so now you
isospastic.
can use this as a representative data in your uh, so now you don't see that pattern in the motion corrected data. So this kind orange pattern is lost in the blue, right? It's means we can't say, but previously if you have looked like it was quite clear
Y-
in this.
Yeah, it
Yeah.
doesn't quite follow it.
So so this is just a check that okay, it has worked.
This one. Yeah.
And if you go down now, yeah, this is exponential fit. So that is isospastic signal.
Exponential fit. Yeah. fit curve to 410
Yes,
signal.
yes. So 410 is completely written. For 470, you have to fill in the blank
If 410 is
somewhere.
isobalistic and 470 is excitation, right?
E. Yes,
Time seconds.
yes. AI. Okay, and then there is a down. You have to select the right data and label the plot.
Yeah.
So, like for again excitation, it is done. Now you have to do it for
Choose the right data
uh,
to plot.
isobalistic.
Fit
Yes,
CH 410.
I means it doesn't matter that much, but
Sorry. Nine.
this fitting takes a little time. Okay, got it, or some error was there? Huh.
So, what, so,
No, no, no. So
so
these are
this
just
step is fitting the
uh,
data, and
parameters
this
like
is what
that
transforming.
you are getting from curve fitting, and now you are so for each time you want to apply that function.
Okay.
So this double exponential function is applying that function, like whatever function you have created, right? Means uh, let's say your function was a a into e to power ax plus b into
Okay.
b e to power bx. So each x is what? X is your time, right? Means here. So for each point that is being applied, curve fitting is the function that is actually doing the job.
Yeah.
So this step is so the function. Yes.
Okay. And what about this step? Oh, it's just applying the function.
Yeah. So this step is very odd sometimes. You see that step in
So
the
this is the fit.
middle, like in the red part, there is a step kind of change. Yeah, means about this one if you see like yeah, this one does not fit very well. So this must also
This
exist
one?
in green. Like it's not very. It may exist there.
Yeah, this
It's
one,
not
this
very
one.
visible.
Yeah.
So these kinds of actually error occur, and sometimes they are such a great extent that you have to analyze the chunks separately. So sometimes like this step changes may occur due to, let's say, you may have changed the intensity of excitation in between the session. So then yeah, while recording, you realize that okay, this is some noisy signal. Then after 15 minutes of recording, you change that.
while recording.
So you have to analyze separate parts, or something may have become loose, which you can't change in with a while recording. Uh, so the signal drops,
Okay.
both the signals together. So then again you have to create. So this is something which disable us to like not mass analyze this, like all the sessions together. I can't analyze. I have to see each one by one. I have to see these graphs, look carefully that these kinds of things should not be main significant. Like, okay, yeah, looks fine. So within like a short time window, it will not change much. But if you, let's say, plot you're in the same cell, you plot it twice, one with x limit of towards the end, something, let's say 1900 or something, and one is this 260. So just no, copy everything, plot it twice. Yeah, plot it twice. Basically, you have two plots.
Twice.
1950 or something you can put, and here 1910. No, no, plot it in that range.
Oh,
Yeah, so here you see that mean value in that short period is okay. It's all. But here the mean value was like 163, right? And previously
yeah.
it was 171 or something, right? 171. So that has changed. And by what percent it
70.
has changed is approximately the same percent of your
Yeah.
increase. So this is one of the sharpest peak that you get, right? These are smaller peaks that you see. So those peaks are around like 5 units. Okay. So the percentage that you get is generally uh,
Yeah.
2 to 4% of percent peaks you get, right? Means generally this is the scale that we get to 2 to 4% or something like that.
Okay.
But
This is the maximum you can get.
now if your mean itself is like from 171 to 165, that itself is uh, 3-4%. So you can't compare the signal directly, you have to scale it down.
Yeah.
So if you either see, let's say, DF, so if you high pass filter this, then everything will be collapsed to mean zero. But then again, the DF height may be scaled according to, like, the DF height at the initial will be, can be 5% bigger than this because of the baseline difference. So that's why we do this DF over F. Next we'll do that. Basically, we got this exponential
Yeah.
thing because we will use this as baseline. So now that is the part. Choose the right values to get DF over F. So you have to
Yeah.
choose the
Okay. So while doing
exponential
DF
thing.
over F,
That is our
so
F.
we use this line or this exponential fit or the actual signal. Okay. The
No, DF over F. What is df? Yeah, but
The FF,
difference from?
it must be difference, right?
Yeah, correct. So it is called df because
Correct.
the high pass filtered one is a
This
df,
one and
already a
motion
df,
corrected one.
df from the mean. You can also take df from the exponential, but a better way to do df is high pass filter.
Yeah.
But that df has some element of movement artifact, so that we correct
So
the df for movement
in this
artifact
step
using
we're
ISO
already
best.
doing that.
So that is actually df corrected. Whatever you have written is FFE motion corrected, that is fine. Yes.
Yeah. And this would be the exponential fit.
Yeah, I think this was the only thing that you needed to change. So you can either analyze df over f, or you can still z-score that and see that
Calculating
as
the
a
z
like
score.
score. So
Okay.
z-score people report because it percentage-wise value seems very low, and z-score can actually give you that it is rare event that it is occurring, right? And you can compare z-score directly from different sessions, different animals. That's an assumption again, like some modern statistical frameworks have actually uh, found that this assumption does not hold true always. Like what people publish is finally z-score, and they average them over sessions, over animals, and say that okay, this is how z-score will behave. But there are some techniques which are better than this to compare between sessions, to compare between animals. They they use some other frameworks. They are complicated frameworks, but they say that it makes it more comparable from session to session, from animal to animal. But this is a valid assumption that has been held true till now in the field, that you compared z-score directly. So that's the most basic you can do, and it's acceptable. So yes. Yeah, we have not plotted that. It will look almost the same, but you can plot. Uh, you can actually apply that
So we
260
have
to
not
270.
plotted the z
Uh,
score.
yeah, this thing. You see this higher peak after that blue line. That is actually a tone or something, right? Means, yeah. Uh-huh.
Yeah.
But that is after tone. The blue line is tone.
Yeah. This corresponds to this
Okay,
one.
then you plot z-score. It will be a very similar plot. Even the
Yeah.
values will match. Don't do the above step, like don't do that. Okay, I can do that. Means it doesn't matter. I'm not doing anything twice. That's more important.
Oh,
Yeah, very similar looking profile. Of course, it will be, but the values also. Because yeah.
yeah. The values are
Also,
little
yeah. So
different.
z scoring has another way to
But
do it.
yeah.
So another way to do z scoring
So
is
this
you
is no
take
longer
the
in
rest
percentage;
period
it's
of
in z
the
score.
animal and take the mean there. Basically, you subset the rest period, like okay, this 2 minutes the animal was not doing anything. So you take that as the mean, and standard deviation also from there. And from using that mean and standard deviation, you calculate the z-score for whole data. That is another way. So then what will happen that while it is pressing, you will always get some positive value of z-score.
Oh,
So you can denote that as movement. Like, okay, it's already positive. So basically
yeah.
everything will shift up in essence.
That would also give higher scores
And
to
yeah,
these
higher score to
peaks.
this piece because the variation might be low there. Comparatively, yeah, that's true. So yes. And from this is your final data now.
Yeah.
You can use this. And now you can have trial leveraged events from here. You can generate many things from here. And you can get
Oh,
plots, many kinds of plots. Yeah. Yeah, this one is just uh, this is DF, right? No, that one is DF, not DF. Yeah, I guess so.
the
DF
one
over
we
F.
plotted already.
No,
This
no, DF
this
over F.
oh, this is just DF. Yeah.
So like you can generate many plots like this. Then you see this. So basically this is for rewarded and this is for unrewarded, and you can these are trial averaged. So yeah. And so the release
The one
pattern
on
may
the
be
right,
different for different
it
neurotransmitters, or
looked sort of
even
like a
if you do
action
calcium one, then
potential
it may
in
look
a
like
very
a,
inverted action
a
potential or
extended action potential. But this dopamine also has a particular release pattern in this region. In other regions, it may be different, but in the region that I have recorded from, it increases very sharply and then decreases slowly. So it will look like an action potential. The first one also looks like that. But since it is trial averaged, it is just the probability of that peak occurring at different points. You get it? So yes, that's it. So this bonus section, like you can try on you by yourself.
okay.
Just ask the AI to do that for you. That try collect the readings from minus 500 to 500 for different trials and different tone times and present it. Something like that you can do.
Yeah.
And yeah, so this will be it for today. If Arushi also has covered this, okay. So thanks Himanshu for attending and actually uh, plotting some new stuff also. I like that. Uh, oh, yeah, come to our lab
Yeah.
sometime.
Thanks for
We'll
the
show
class.
you some
I mean,
animals and results
it's a
also.
good experience.
Yeah.
Uh,
Okay. Whenever you come for some seminar, like just drop by. We'll see. Okay.
yeah,
Thanks.
sure.
So next week I will start this electrophysiology most probably I will prepare it this weekend.
Yeah, yeah, sure.
And for two lectures, we'll do that, and then Deepak will take over. Okay. Okay. Thanks. Bye bye, Arushi and Manj.